So in this video, I'm going to talk about Cartesian products. I will include two different definitions and maybe compare them a little bit and then discuss in what scenarios that we prefer to use, like in which scenarios that we prefer to use the first definition or the second definition. Okay, so suppose that we have X and Y. So here is I'm gonna introduce the first definition for the Cartesian product. So if we have the set X and Y, then the Cartesian product of X and Y is defined into this is equal to X, Y, which one? This one is ordered tuple, where X is in X, Y is in Y. And of course, if you have, for example, you want to do the Cartesian product of x1, x2, dot, dot, dot to xn, where n is finite number, this is equal to a set of ordered n tuples. So this just follows the definition for the above one. Sorry, so this should be x1 in 1 and xn in xn. Okay, now what if n here becomes infinite? It doesn't make sense to write an ordered tuple where you have like infinite many elements. So because it could get messy and hard to explain, we need to adopt the second definition in that scenario. So for example, let me define an index set A to be just a set of alpha. Sorry, let A to be indexed to be our index set. So each element in A denote to be alpha, and this A could have infinitely many elements. Okay, and our Cartesian product, I'm not going to write a long one, but I'm just going to adopt the short notation. So alpha is in A, x alpha. That means this is equal to x alpha 1 times x alpha 2 times dot, 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 and we don't know the length. We don't know the coordinate of A, so that could go forever. Okay. So this is equal to, so here we're not going to use the tuple anymore, but we're going to define a different way. So this is going to be a set of mappings F. So notice that it is a set of mappings. I'm not saying this is equal to just one mapping. I'm saying this is a set, a collection of mappings. If you want to, also use the term functions or maps. So this is a collection of functions. And then, of course, there are some certain properties or categorizations for such functions. And here I'm going to introduce. It is a set of mappings F from A to the union of alpha in A of x alpha for every alpha in A. So the last sentence is very important because it tells you that, okay, for example, let's just focus on one element F in the Cartesian product. Okay. So what I'm saying is F is not a scalar valued function. F is actually, you can think about as a vector value. So you need, so for example, F, I'll need to define F to be F alpha 1 to be X alpha 1 to be something in X alpha 1 all the way to f alpha 2 to x alpha 2, f alpha 3, using x alpha 3, da, da, da. And notice that here, because I want to let you know the formula of f explicitly, I write it out in this way. But in practice, it doesn't have to be ordered in by the natural number. It could be, I don't know, like alpha could be real number. So maybe here, not alpha 2, but a different number that is a little bit larger, or any number that is a little bit, that any number that could be different than 1. So it's just like illustration, like how, or this A could also be rational number. It could be any set. But the idea is when you define a single element in the Cartesian product here, you're not defining just one, you are defining many. You're defining for every alpha in A. So that is the key thing. And that is the definition. And let's compare the first one and the second one a little bit. So I'm going to show you an example and then write out in 2 different ways. Okay, so let x is just er and y to be z. Okay, so if we use the first definition, the Cartesian product x times z is going to be equal to r z, r is in r, z is in z. Versus if you are using the second definition, we're going to do is still r times c. And I want to emphasize here, the second definition is really useful when you have a set A that is much more complicated, much more complicated than just the natural numbers. So of course here we have n is equal to 2, and of course we can represent this Cartesian product using the first definition. And then the reason that I'm using the second definition on this simple Cartesian product is to show you the difference between the first definition and the second definition. But in practice, the real advantage of using the second definition is when A is a complicated set. So the cardinality of A could be infinity. So that makes sense by using the second definition. Okay, so let's go back and focus on showing the difference between the first and the second definition. So if we have this, and this is going to be a set of mappings F, where F is defined to be from, so here I can let R to be my x1, let Z to be my x2. So it's going to be from 1 to R union Z. And for for 1 and 2. So what I mean is, so let's focus on specific element in this set. So F, for example, I just put an example. F could map 1 to 0.5, and F could map 2 to 2, and this is what one element belongs to this Cartesian product. This is one function. I can write a different element in this Cartesian product. For example, I can write F1 is equal to 0.3, F2 is equal to 6, right? And this is another element in this Cartesian product. And this is, you can think of this as 0.52, you can think this is 0.36. And notice that those tuples are the familiar ones in this collection. Okay, I hope you have a better idea on the difference between the first and the second definitions. And I think in Folland chapter 4, or anything that the measure theory related to the product measure will use definition. We'll use the second definition. Thank you.